All right, let's talk about something that's all around us, but is completely invisible. I'm talking about these hidden energy landscapes created by electric charges. Today, we're going to map out this unseen force field that, and I mean this, literally powers our entire modern world.
So let me ask you a question that might sound a little weird. What on earth does a planet sailing through space in its orbit have in common with that tiny little static shock you sometimes get from your finger? Well, the answer is all about stored energy. Believe it or not, the same fundamental principle is at play in both.
And here's the game plan for connecting those dots. We're going to start with something we all get, gravity. Then we'll use that to see how energy gets stored in these fields. We're absolutely going to clear up the difference between potential and potential energy, because that can be tricky. And then we get to the fun part, actually mapping these energy landscapes, first for a single charge, and then for something called a dipole.
Okay, so to really get a handle on this, let's start with something we all know intuitively. Just picture yourself lifting a book off a table. You're working against gravity, right? But that effort you just put in, it isn't gone, it's now stored as energy in that book. That one simple idea is the key to everything else we're about to dive into. Now, the whole reason you can store energy that way is because gravity is what physicists call a conservative force. It sounds a little formal, but all it really means is that the path you take doesn't matter. You could lift that book straight up, or you could wander around the room with it before putting it on a high shelf. The amount of energy stored is exactly the same. All that work you did is now potential energy.
So yeah, gravity is a classic example. So is the force from a stretched spring. And here is the crucial link for us today. The Coulomb force. You know, the force between electric charges, it's also a conservative force. And that changes everything. It means we can think about storing energy in an electric field in the exact same way we do with gravity.
So if the electric force is conservative, well, that lets us define this new thing called electrostatic potential energy. Let's really break down what that looks like. Let's do a little thought experiment together. Imagine you have a big positive charge, let's call it Q, and it's just sitting there, fixed in space. It's creating an electric field all around it. Now, you come along with a tiny little positive test charge, Q, and you decide you're going to push it closer to the big one. We all know like charges repel, so pushing that little Q closer is going to take some effort. You have to work against that repulsive force. But just like when you lifted the book, that work you're doing doesn't just vanish. Nope. It gets stored as electrostatic potential energy. And if you were to let go, poof, that stored energy would instantly convert into motion as Q flies away. So here's the key takeaway. The change in potential energy is simply the amount of work it takes you to move a specific charge from one spot to another. And notice, this depends on two things, the field itself and the size of the charge that you're actually moving.
And this brings us to a really, really crucial leap in how we think about this. We're about to shift from talking about the energy of a specific charge to talking about the energy landscape of the space itself.
I mean, think about it. So far, our potential energy depends on the charge we're moving. A bigger charge means more work, more stored energy. But what if we wanted to create a kind of energy map of the area? A map that exists whether we happen to place a charge there or not? How would we do that? Well, the solution is surprisingly simple and kind of elegant. We just divide by the test charge. Instead of talking about the total work, we talk about the work per unit of charge. This new quantity is called electrostatic potential, and it's a property of the field itself. And here's the really cool part. This is what voltage is. When you see volts on a battery, you're looking at a measure of this very energy landscape. Think about what this really means for a second. The potential at any single point in space is the amount of work it would take to bring a standard 1-unit positive charge all the way from infinity to that exact spot. It's a number that basically tells you how much energy is waiting at that location in the field. Okay, we have our new tool, electric potential. So let's use it to map out the simplest possible energy landscape there is, the one created by just a single solitary point charge. And the relationship is beautifully simple. The potential is directly proportional to how big the charge is, and it just gets weaker the farther away you are. So a bigger charge creates a steeper hill on our energy map, and that hill gradually flattens out as you move away. Now, what's fascinating is how this potential compares to the electric field itself. As you can see here, the potential, that's the blue line, it drops off pretty gradually, but the electric field, which is the actual force you'd feel, it plummets much more quickly. So you can think of it this way. Potential tells you the height of the hill on our energy map, while the field tells you how steep that hill is at any given point.
But, of course, the world is way more complex than just a single charge. So what happens when we add a second one? Well, that brings us to a super important configuration called the electric dipole.
A dipole is just a positive charge and an equal opposite negative charge held a small distance apart. A water molecule is a classic example, and these dipoles are absolutely everywhere in nature and technology. And as you can guess, this simple pair creates a much more intricate energy landscape. And how do we map this more complex landscape? It's beautifully simple. We just add them up. The potential at any point in space is just the potential from the positive charge plus the potential from the negative charge. This incredibly powerful idea is called the superposition principle. And when you combine these two charges, you get completely new behaviors. Unlike a single charge, a dipole's potential actually depends on the angle you approach it from. It also gets weaker much, much faster as you move away. And amazingly, there's an entire plane right between the charges, where the positive and negative potentials perfectly cancel each other out, creating a line of zero potential. And the simple idea of just adding them up, the superposition principle, it doesn't just stop at two charges, it works for any number of them. This is the tool that allows us to map the energy landscape for any arrangement of charges, no matter how complicated it gets. So let's just quickly recap our journey here. We started with the familiar idea of storing energy against gravity. We saw that the electric force works pretty much the same way, which led us to find potential energy. Then, by dividing out that specific charge we were moving, we created a map of the field itself, the electric potential. So, we've learned how to draw a kind of topographical map for electricity, where voltage is the height, and charges naturally roll downhill. So the final question is, how does mastering this invisible terrain allow us to build our entire modern world of electronics? Well, that's the power of understanding potential.